Welcome back to the Open Generation 5G Summit. Layla and I hope you were able to join us for the opening session and had a good break. Maybe you had a chance to refresh your coffee, catch up on your emails, maybe do a meeting or so. Are you ready now for our next breakthrough session? We hope so. Layla, before we jump into things, I'd like to understand more about the approach used by Open Generation for our 5G use case innovation.
Yes, thank you, Ajit, and welcome back, people. So when we talk about use case-driven collaboration, it means we are focusing on enabling use cases that are relevant to society and where current barriers may be overcome with 5G new capabilities. So we start by identifying the priority use cases and what are their corresponding challenges and requirements. And we move to identify architectures that support each use case and solutions for implementation. Then we collaborate to launch initiatives for experimentation, including test beds and simulation efforts. And as a result, we can contribute, for instance, to standards with results from the experiments, refined requirements from the use cases, and proposals for innovative solutions. So in this session here, we are going to focus on the use cases, which is the first block in this picture, and the potential of 5G to enable them. And I would like now to transition back to Ajit, who will introduce our speaker. Hello.
Network product solutions for Ericsson North America. Paul is responsible for radio products, including IoT and Open RAN, and he currently serves as Vice Chair, Board of Directors of the CBRS Alliance, and on the Board of Governors for 5G Americas. Thank you for joining us today, Paul.
Thanks, Ajit, and hello, everybody. And so today I'm going to talk about use cases. And so when MITRE talked to me to say, okay, can we say a few words about use cases? It really struck me as to how impactful that use cases have been in our society and our lives. So if we want to go to the next chart, please. All right, yeah, so you start there, okay. And so if we think about 4G and 5G and 6G, we've had an evolution path between 4 to 5 and shortly 6. So in our 4G world, I'm sure your device is like mine, where we have great capabilities for banking and social media and vacation booking, all those great things that we take for granted every day. It is our most critical personal tool and our most critical business tool. But really, as we move to 5G, that wasn't the intent. And although each of those applications become faster and better and more reliable, that wasn't the original intention of 5G. And so as we have networks deployed now, we see that 5G is contributing in many other areas that are really important to society. So for example, if we look at the digital divide, so as we deal with 20, 30 million Americans not having appropriate internet connection, closing this digital divide is really important. And so 5G fixed wireless is a good mechanism to do that. If we look at e-learning, for example, we sent 50 million students back home to do e-learning, and 5G enabled them to have a better experience with their e-learning. Healthcare in our COVID times become more and more important, whether it's COVID related or for the elderly, that's critical. Public safety, so things like FirstNet with AT&T have become a very important network to deal with our first responders and to keep them out of harm's way. And then if we look at Industry 4.0, so of the 300,000 or so manufacturing locations around the US, 5G enables those to be more effective, more automated, and more competitive, along with all the IoT, the Internet of Things capabilities. Of course, it allows us to enable autonomous vehicles, autonomous drones, of course. And then in these days, it seems more important than ever to keep ourselves entertained, so immersive entertainment. So all of these applications are then brought to life with 5G, as well as the underpinning and economic advantages. So the GDP growth and the new jobs that are created with 5G. And now as we look forward to 6G, although it feels a bit too soon to be talking about 6G, so maybe we'll call it beyond 5G. If you look at what's going to drive that, so the applications drive that, and the applications really demand limitless connectivity. So regardless of where I am in the world, whether I'm on a desert or in an ocean, that I want to have that high speed, low latency, high reliability connectivity, so limitless connectivity. But as our network experience is more and more entwined with our everyday life, trustworthiness and security becomes even more important than it has been before. So that's something that needs to be focused on. And the expectation is that 6G helps us with our sustainability goals. And in fact, the 17 UN sustainability goals are something that 6G will contribute to. And then, of course, overall, we want to make sure that our lives are made more simple and simplified. And that's another key goal for 6G. So that's how we move from 4 to 5 to 6G. So if we look at the next chart. So then I look back at what I used to say about 5G a few years ago, and let's say we're in year 2, maybe year 3 of 5G. I used to talk about a chess set, and a chess set of having the different pieces represented different capabilities of a 5G network. And as we move from, say, 100 megabits per second to 10 gigabits, that would be represented by the king. For example, latency would be the queen, and reliability and security would be represented by the rook or the castle. And so we had a set of aspirational targets for 5G, which I'd argue we've delivered on pretty well. So if I look at downlink throughput, we move from 30 or 40 megabits per second to much higher rates and probably 2-3 gigabits per second on a commercial basis now, right? So not quite 10, but we're getting there. And then in terms of latency, in the US, it was typically 30, 40 milliseconds. Actually now with 5G, we're hitting less than 10 milliseconds round trip delay. So all these parameters are being delivered on, and the chess set is then used to deliver applications. And so when I look at the set of applications that we used to talk about a few years ago, we talked about augmented reality, virtual reality, cloud gaming, the Internet of Things, and making our cities smarter. And I would argue that we've delivered on the majority of those. Also, autonomous vehicles, we said autonomous vehicles, whether cars or drones, would be a key focus area. And if we go to the next chart, so if I dive down into this in our Ericsson's work with Open Generation, we've been working in the working group around use cases for drones. And so we picked out 4 key use cases, and you're going to hear a lot more about these on the panel upcoming, I think. And so we picked out commercial package delivery. So imagine pizza delivery or grocery delivery from drones, but not just one proof of concept or one trial. How do we scale that to tens of thousands or hundreds of thousands of drones delivering packages across the US? And so then if you look at the challenge there, we see somewhere between the 200 feet limit, which is above the radio clutter, and below the 400 feet that the FAA tells us to stay below for drones, that we need to make sure that we engineer the network for great drone performance. And so we can do this on 4G, but 4G takes a toll in every drone that we put onto a 4G network. It really kind of drives a big capacity demand. So in 5G, we can use the beamforming, beam steering capabilities to give a better experience for that drone compatibility. And then it allows us to move from a private network to a public network, from, say, warehouse over to the airspace. So these are things that we're working on in terms of commercial delivery. If we look at the emergency response perspective, then one of the key things here is to make sure that we keep our first responders out of harm's way. And so one of the key things to do is to provide high quality video, low latency, high reliability for a video over whether it's an accident scene or a fire or any emergency service location. And so we are making sure that we have a network architecture that will be able to deliver that reliably for the emergency services. Then the 2 other use cases here are around inspection. And so fixed infrastructure inspection. And so that would mean, for example, looking at the electricity line, so electricity infrastructure, so inspecting those to make sure that they're well maintained and functional. And then potentially cell site is something we use today with Ericsson drones. We inspect cell sites to make sure that they're working properly. And then the final case is looking at indoor inspection. And so that's, imagine a warehouse and looking at the indoors of that warehouse, and you have a set of inventory there. So using a drone to look at the inventory and see what inventory levels that you have. And so these are the 4 use cases that we worked on, and we're pushing and driving to define these technically from an architecture perspective and allowing these to be scaled commercially to push the envelope of 5G. Next chart, please. And then if we look at how that fits into a 4 and 5, 6G model, I mean, 4G drones, we had potentially it's a pilot driven, it's a line of sight pilot being used. The network connectivity is potentially the payload. So the video being distributed is actually the payload of the drone. Maybe that's on a 4G network. But again, as I said before, it's a capacity demand that we're trying to manage. In 5G, we move the command and control both to the 5G network. So now I can remotely control the drone. I can fly it through predetermined flight paths, again, dependent on the FAA regulations in force at the time. So I can then do longer distances and control that drone for both payload and control. And so you have a picture here of in the middle bottom right is the inspection of electricity power line, for example. But then as we look out into 6G, there's more fun use cases there in terms of the air taxis, for example, unmanned air taxis. And then my personal favorite on the bottom right is actually a QR code composed of drones in the night sky. So imagine that you can use your device, you can look up to the night sky, click on a QR code, which is composed of drones in the sky. So that's a particularly fun one. Next chart, please. And then in case you're thinking, okay, well, what really exists? What's the real reality of the situation? I thought I'd pick up a use case that we've done ourselves here at Ericsson. We are using, and we constructed a factory, about $100 million factory, 300,000 square feet, just down the road from where I am in Texas. And we have use cases there where we have drones being used for surveillance and security purposes. We also have drones using the indoor inventory checking kind of process as well. So that's being done today in real life use cases. And that's fitting into a system in the factory where we have components coming in to make the 5G radio. So using 5G to build the 5G radios for our networks. And so those robots delivery systems take the component to the production line. It's constructed in the production line. It comes off the production line, is inspected by augmented reality and virtual reality to know that the radio is good before it's shipped out. And then this is actually delivered over a private network, and so that we have cloud capability, we have an edge compute capability. So really this is an end-to-end challenge. So it's private networking, end-to-end, bringing cloud and 5G together to utilize and deliver a great use case experience. Next chart, please. But if we move beyond drones, there are many other use cases that 5G contributes to, and one that I particularly care about is the digital divide. And so the FCC says it's about 14.5 million people. Some of the surveys say 75 million people in the US don't have appropriate internet connectivity services. And so this is really unacceptable. And COVID really taught us that there's a real challenge here as we send everybody home. And then particularly in the student case, so I talked about the 50 million kids now back at home doing e-learning. What we forgot about was the teachers. So the 400,000 teachers themselves, that's about 10, 12% of the teaching population, they themselves didn't have great internet connectivity. So what's the big deal? Okay, if I don't have great connectivity as a student, what does that mean? Well, it can impact your grade point average by up to 0.4. That's a big deal if you're trying to get into college. And this isn't just a rural experience, this is also an urban thing. And so 20% or 21% of the urban population also has challenges in terms of connectivity. So what's the answer? So fortunately, we see there's a piece of legislation going through right now, the infrastructure bill, where $65 billion of money funding is allocated to building this infrastructure, of which $42.5 billion is actually for the building part. And it's a technology neutral fund. And we look at 25 megabits down, 3 megabits up, or 100 megabits down, 20 megabits up as the sort of two thresholds. And that puts it well within the capabilities of fixed wireless access to deliver these. And so although there'll be a lot of funding that goes to fiber is, of course, great capability, but really even $40 billion is a drop in the ocean in terms of connecting the entirety of the US over fiber. And so wireless capability is important, and we have a number of different capabilities in fixed wireless to be able to deliver that. So CBRS, which is 150 megahertz of spectrum, that can deliver maybe 100 megabits per second or at 7 miles out from the cell site. And so that's starting at 4G, moving to 5G. So that's one option. We have mid-band spectrum that can go up to 300 megabits per second, say. And then we have the kind of big guns of millimeter wave, where in an urban environment, that's maybe 1 or 2 gigabits per second. If you're really stretching it out long range in a rural environment, that's maybe a gigabit per second. And so then what does fixed wireless look like in the 6G world? Well, we don't know yet, but maybe use of some of these new metamaterials on the roofs of farmhouses, maybe that's going to lead to something interesting. So this is a key part of solving the digital divide. So 5G and then the future 6G. Next chart, please. But the digital divide is not just about connection to the farmhouse or the rural building. It's about connectivity, mobility connectivity. So we don't want to exchange a digital divide for a mobility divide. So we want to make sure we have good mobility coverage. And why do we need that? For the 2 major industries in rural, which is manufacturing and, of course, agricultural. And so in the 4G world, we have examples today of 4G IoT services being used to make farmers' lives easier. IoT connections to enable and optimize irrigation and connectivity. And we have the connected cow, for example, so things like that. In 5G, though, we bring the high-speed nature of 5G to bear, and that allows us to do high-speed video processing. And so you see an example here of crop inspection, where you have a video camera looking at crops that's sent back to the cloud, analyzed for any pest or fungal issues, and then drones can be deployed to treat the targeted area in a precision sense. So this is what precision agriculture is. I don't need to do the whole field. I can go and specifically target for pests or fungal infections from that drone specific location. And so precision agriculture is going to be really important for our farmers going forward to make agriculture more efficient, and also to make sure that we have a more sustainable way of farming. So that's quite a bit of transition in agriculture. We also can use things like the connected herd. So each livestock, each cow, for example, can have an IoT device and be tracked. And then we have things like agricultural robots, which is a tractor, for example, then can be unmanned and sent around the field to do farm work without the need of human intervention. So many advances in the agricultural world. And next chart, please. And so then the obvious question is, okay, in terms of 6G, so what's the chess set available for 6G? And how do these pieces become stronger or more powerful in the 6G world? And so I kind of took the easy way out here and put to be defined in terms of our 6G parameter set for these chess pieces. But if you can imagine, I'm at 100 megabits per second for 4G, multiple gigabits per second for 5G, then clearly 6G has got to exceed that. Is that tens of gigabits? Is that 100 gigabits? Is that terabits? That's something that's being defined. The expectation or the demand is that latency should be sub-millisecond. So we talked about that a little bit in 5G, but 6G could realize that sub-millisecond capability. And then, of course, increment the reliability and take on the good work of ultra-reliable, low-latency communication in 5G and really bring that to life to the next level in 6G. So again, we're going to have a very powerful set of chess pieces to deploy in our 6G world. So if we look at the applications that this will enable, then is one of the big ones is a family of use cases called the Internet of Senses. And so maybe the most straightforward one is vision. So how do I have each of my senses then interact with the network in a deeper way? So in terms of vision, that would be augmented reality or virtual reality. And then in terms of the sense of touch, that would be the world of haptics, or the world of the tactile internet. So you imagine you've seen haptic suits, so they would be brought to life. Connected intelligent machines, the world of robotics will advance significantly, and the use of cooperative robots or cobots in factories will become wide scale. And so the world of robots will meet and intermingle with the world of the network in a much deeper way. Digitalized and programmable world, think about digital twins. So that's something that we'll talk more about in a second. And then in terms of sustainability, this is way more than breaking the energy curve of the network today and making the energy efficiency of delivering bits better. If you look at 5G over 4G, there's a 40% advantage of reduction in energy per bit of 5G to 4G. But this goes far beyond there. And one of the discussions is around having an application called the Earth Monitor. And the concept there is to have billions of sensors on a planetary basis, feeding back information so we can manage the environment in a much better way. managing temperature rise, managing the environmental quality, and all of these things brought together in a concept called Earth Monitor. So a really exciting set of applications that could come together in the 6G world. Next chart, please. And so I talked about digital twins. And so maybe you've all seen a jet engine, maybe modeled as in the digital world, and you can do things in the digital model and see how that performs in the physical world. But 6G allows us to move much further down that cyber physical continuum. And so it's not just a jet engine. Maybe it's the whole airplane. Maybe it's the whole smart city. Think about interacting with your favorite highway that you commute on. Imagine if you can predict the exact traffic situation when you arrive on that highway and your exact journey time. So much deeper interaction, much more progressive cyber physical activity. And so if you think about the fundamentals of the cyber physical world, there's a lot of data moving backwards and forwards between those both worlds, putting more and more strain on the network. Imagine you modeling an entire smart city, how much data is moving backwards and forwards. And so again, that drives you to new sets of network architectures and approaches. Next chart, please. And so in 5G, we really talked about latency a lot. It's the first time we really ever did have a discussion about it. And it's translated maybe in the consumer world to a more reactive or responsive application. And we moved from tens of milliseconds in 4G to that maybe less than 10 millisecond in 5G kind of capability that we're achieving today. And then if I extrapolate forward, then if I really hit this sub-millisecond world, what does that enable? And so that takes us to things like holographic interaction. And the thing about a hologram is very high data rate, hundreds of megabits per second or maybe gigabits, and a very tough latency requirement. If I want the hologram to move and interact with me, then I don't want to have any latency. And then, of course, if I have a haptic suit, if I'm playing basketball with my haptic glove, I have to have instant response. I can't have any lag in this. So latency will be really important in subsequent generations as well to enable yet more use cases beyond just the kinetic use cases that we have in 5G. Next chart, please. And then, so back to entertainment. So if we think about what we can do today in 5G, most NFL stadiums have great capabilities here. In my local stadium is the Cowboys Stadium. So you can go to the stadium and see augmented reality capabilities. And so you can see there's a 40-foot Dak Prescott sort of with your augmented reality device standing in front of you. So very cool capabilities that you see, an enhanced fan experience. You can have multiple video streams of different player angles and player cams, and that's relatively mainstream today. And then in the bottom middle there, you see an example of a interview we did actually with AT&T and ESPN, where we brought an NBA basketball star and had an interview with him before a game when he wasn't able to travel because of COVID restrictions. And so that is a real life broadcast TV holographic image being used in an interview. So that's pretty cool. And then as we see, that extends to much more interactive experiences where I could go into an environment where I have, in a multiplayer sense, that I can interact with my favorite soccer or football team. I think this is a Paris Saint-Germain soccer team interaction there in the top right. So imagine the processing required for that and the amount of data that's moving around and the latency requirement. And then bottom right there is digital smell. And this is, another fun use case here where, it's another part of the Internet of Senses where I can take a particular odor from another location and then transport it back to the location that I'm in and have that sort of odor experience as well. So you have to use that carefully. There's a time and a place for that. But I think that's sort of a wonderful augmentation of the senses in the network. So this Internet of Senses concept comes back again. Next chart, please. And then telehealth, if you look at the 456 transition there, we go from fairly straightforward transmission of patient records around the place, the files aren't so big. Then we move up to much bigger files. So MRIs and X-rays being transferred across the network with higher capabilities. And then we have the advent today of teledocs and basic telemedicine. But then in the 6G world, imagine now the bedside manner of a hologram. So I can have a doctor in front of me with a holographic presence, taking in inputs from the digital network, but giving me some bedside manner accommodation in my hospital bed or at home. And then in the bottom right here, 5G often talks about remote surgery as sort of a poster child application. But I think in 6G, the capabilities of remote surgery, I think, come to life and become more and more extensive. So lots of great extensions in e-health across the generations. Next chart, please. And I mentioned before that the robotic world will come much more into contact with the network. And so from basic simple robots, we move to much more sophisticated robots over time. And so there's a picture here of a robot dog equipped with 5G. These can then roam around airports, for example, doing surveillance. We have one of those in our offices in Plano where we can kind of moving around. An example that in the top middle, the pink autonomous vehicles there, that's actually an example in Toronto where they're food trucks, actually autonomous food trucks that move around Toronto delivering great food, I'm sure. And so that's entirely autonomous. And then as we move to 6G, we see things like enabling a contact lens to have digital data superimposed upon it. So today we think about glasses or spectacle formats, but imagine that in a contact lens format. So great capabilities there. So robotic and image enhancements and human augmentation all coming to play in the evolution of a network. Next chart, please. So as we build out all of these use cases, it is really important to have the architecture and the network set up correctly. And so we need to do two things. One, to make sure we have open architectures. And the second is that we have the right level of automation. So in the sense of open networks, we want to look at building that in a virtualized manner. And so we spent the last 10 years probably moving the core networks or the core part of a network into the cloud. And so that journey has happened, still happening actually. And the next step is to take the radio access network and then move that into the cloud. And so that's happening with RAN virtualization. And so that allows a softwareization of the network, a programmability, our ability to scale capacity and move around in the network. And on the right-hand side, we see automation. And networks are so complex to manage. Many thousands of parameters that we're continually trying to optimize to give a great user experience. This has to be automated. And we have to create platforms that allow AI and ML to help us with that task. Not only to manage the network and not only to create cost efficiency, but also to be able to generate new services and new capabilities. And so we have APIs and ability to add apps to then control the network. So from the application layer to the network, we have a lot more capability. And then in the middle picture here, I love an icon that I love. That's the half brain, half robot, which I think will become emblematic of the kind of 6G discussions. So automation on an open network architecture are really important, and the flexibility to create more and more new services and new applications. Next chart, please. Next chart, thanks. I think you're stuck on the chart. Can you move along? Yeah, I think you're stuck on the chart, or maybe after. Let's see. So the next biggest thing is all of these applications and all of these life-changing experiences really need to ensure that we have security underpinning them. And so one of the big trends right now is to make sure that we have a zero trust architecture. And what that means is that you don't inherently trust any part of the network. And just because it's within my firewall, I don't necessarily trust it. And so we need to implement that architecture going forward. And so whether it's through authentication, mutual authentication, multi-factor authentication, different strategies for protecting the network, that all has to be done because it becomes more and more critical in our lives. There's another interesting thing, which is something called RF fingerprinting. And so RF fingerprinting is really, we know that each radio in the network has a specific characteristic, and those tiny imperfections of the radio are actually detectable. And so what we can do is create this radio fingerprint to make sure that we have a a defined relationship between the radio I think I'm talking to and the actual radio that is actually communicating with. So RF fingerprinting will be a really interesting technique that we'll be able to use for security going forward. But security and trustworthiness, really important. If you want to go to the next chart, please. All of these use cases create a tremendous economic growth and acceleration in the country. And so if we look at 4G, for example, in the CTI study from last year, somewhere between $200 billion and $700 billion of economic impact, with 17 million nearly jobs created as a result of 4G. And then our latest study right now, looking at for 5G, that impact is 1.5 trillion. So more than 2x that contribution, and maybe 4 or 5 million jobs created. And so then the question is, what will be that multiplier factor in 6G? I think it's tremendously exciting to see that, and as we define that over the next decade. What's important is thinking about that this is a national infrastructure, and that national infrastructure is an important piece for US competitivity. And so really making sure that that's in place is super important. Conversely, any delay in that rollout is really not a good thing, is very damaging. And so currently we're saying every 6 months, that's a $25 billion impact on lost economic growth. So it's very sensitive to rollout delay. So we really need to make sure as a nation that we have all the elements in place to better roll that out in a good way. Next chart. So just to, in conclusion, a big source of pride and motivation for me is our contribution to building this infrastructure. And really everybody on this call is contributing to that. And so whether it is you're climbing the tower or writing software or contributing to the digital economy, it is incredibly important. And I like to look at this 1934 picture where you have these guys sitting up on a girder over the Rockefeller Center. They have different health and safety rules, I guess, at that time, but they were building the physical infrastructure for the US in the 20th century. And on the right-hand side, I think we as an industry are building that equivalent infrastructure that will ensure US competitivity for the years to come. And it's incredible, important activity. And in a decade's time, we'll look back as to how critical and pivotal this work was. So I'll stop there. Thank you very much. And back to you, Ajit and Leila.
Thank you, Paul.
Thank you.
Leila, any takeaways from Paul's?
Oh, yes. Thank you so much. This was a great presentation, Paul. So you mentioned several things that were very interesting. One of them, but at the end, just a look at those folks sitting at the platform. That's what we have been doing. And I've had the analogy in my mind of us sitting in the work groups and trying to develop this together. That's the platform that we are collaborating with right now. So wonderful. No, so several things came to mind on the importance of 5G and the importance of 6G coming next, and all the set of opportunities and use cases that this brings. One thing you said on the loss of in economic growth that any delay would cause, I would say, agreeing with you that that's why we are here, because we are here to collaborate and accelerate 5G. So to avoid that loss and to increase the economic growth that you alluded to. So Ajit, if you have other takeaways you would like to share.
Yeah, I personally love the chess set analogy that Paul brought to the forefront, and how he connected all the pieces to the different capabilities that are coming with the 5G network. And of course, watch that knight and the positioning, because he's the very important piece on the chessboard as well. And I also love the QR drone use case. That was fascinating. I don't think I've seen that one before. That's a great one for
very cool.
Thinking how you can send QR codes to mass population, and just in general, obviously from the security and integrity of the network, the zero trust network is super important in 5G to ensure that all the data that's being transmitted is secure and unencryptable, or being able to be discovered by those that we don't want to see looking at our packets. So, and then in the beginning, the online learning, that's such an important, especially in this day of COVID-19, a really important facility that 5G will help for the future to allow both students and teachers to be able to have coverage and high bandwidth connectivity through fixed broadband wireless.
Yes, excellent. So next, we would like to introduce our next speaker. I would like to introduce Marcus Weldon. Marcus is the former president of Bell Labs and corporate chief technology officer for Nokia. And Marcus is a technology and scientific leader with the ability to define and execute on a compelling vision of a better techno-economic future across an extraordinarily broad array of subjects and domains. Marcus is currently working on his next big thing and helping several small, medium, and large companies and institutes formulate their technical and innovation strategies for the next industrial revolution. Welcome, Marcus.
Hi there. Good to see you all. And thanks for the introduction, Leila. And thanks, Paul, for a great presentation. It was all-encompassing in many ways. So what I thought I'd do with this panel, and it's a great panel, and I'll introduce the panelists in just a little bit. I'm going to have a few slides to set up the debate we're going to have. And the debate is whether or not, if we could go back in the slides, auto slide produce, there we go. Is UAS the defining use case? And so Paul went through a whole bunch of use cases, and what I'm going to argue, and this is sort of a very classic way I like to think, is there a all-encompassing use case that if we can solve for, we can derive all other use cases from it? And of course, the danger of doing that is if you can't solve that use case because it's too exotic, then you get stuck. But I think we're going to decide and hopefully convince you in this panel today that we can solve the UAS case, and in short order by working together in OpenGen consortium and with all the participants we have. And if we can solve that case, we can derive all the others because they're lower dimensionality, simpler spectrally, simple in terms of information content than the UAS case. So that's pretty exciting. And it also justifies why OpenGen is right to focus on UAS. It's not too exotic. It's just the right level, I think, of exoticism and to solve for all the important use cases. And that will remain true in the 6G era too. So I'm going to try and set up the debate a bit with a few slides. Some of them will touch on what Paul has talked about, and some will extend some of those points, and maybe a couple of new points. So if we now move forward to the next slide. So first of all, you should answer the question, what is it we're trying to solve for? Because we've got that whole set of use cases. Paul's are quite exotic in part and quite tangible in others. But in the end, I think it all comes down to what we're solving for is declining productivity. So in the first and second industrial revolutions, you saw this nice purple bars of Robert Gordon's book where productivity growth went up. But ever since then, in the internet age, and that includes the early phase of 5G, productivity growth has been diminishing. And it, frankly, it's because we've focused on consumerist use cases. And that's media, entertainment, some financial services, etc. But we haven't digitized the physical world. And that's the hard problem we have left in front of us is what commonly is called cyber-physical connectivity. But it really is digitizing every aspect of the physical world. It is roads and factories and warehouses and cities and drones and imaging and understanding that and then making sense of it. Once we've made sense of it, of course, we can then take actions based on that. So I'm going to argue that productivity is the thing we're actually trying to solve for in all its forms. And that's not a trivial thing, as Paul Krugman says here. It isn't everything, but in the end, it's almost everything that humans ascribe to or aspire to trying to achieve. So that's the big problem. And I'm going to argue that that UAS and that set of use cases is the high order bit in solving the productivity problem. So if we move forward, this is just a pictorial now depiction of the 4 industrial revolutions to date. And I want to explain how the physical world was always part of them. And in fact, digitizing some part of the physical world and augmenting that was always part of them. So if we start with the first industrial revolution, it was about building human assisting machines that gave mechanical advantage so humans could essentially perform tasks that would be on their physical capabilities. So it's the first form of trying to mechanize the world, which you think is mechanizing the world is an early form of digitizing the world. It was just more mechanical rather than digital at the time, but it's assisting or coupling to the world in a new way to obtain mechanical advantage. Second, Industry 2.0, or the second industrial revolution, was all about then doing something similar, but now over extended distances. So the machines didn't just locally produce or enhance, they were able actually to move themselves across domains and across infrastructures and create infrastructures. So we now had extended capabilities that became mechanized and started to digitize. That's where you get the early connectivity networks, etc. Because as those infrastructures could be built, assisted by machines, of course, we created communication as well as transportation and logistical networks out of that. So we start seeing the beginning of the digitization and digital interconnectivity of the physical world. Industry 3.0, of course, was meant to take that much further. The internet or web age, I think, was meant to digitize the physical world well beyond media, entertainment, and financial or e-commerce systems. But we stopped short. We got a little bit stuck, in my view, with smartphone addiction, which led to a set of applications and tools that, although compelling, don't really manifestly increase productivity. In fact, you could argue they're what we do when we're trying to be unproductive in some cases, or if not trying, succeeding. So now what we have in front of us, and this is the 5G and 6G era for sure, is finishing what we started. And Industry 4.0 is about that. It's about digitizing the entire physical world, the part that's beyond media, entertainment, and financial systems. And that's a harder problem, of course, because it's remote. It's in inaccessible places. It's dense. It's hard to compute. The physical world is something that humans are expert in understanding and machines are relatively inexpert in understanding. So we've got to solve for a large set of problems to do with human access to information about the physical world, sensing it. We've got to connect all those sensors, as Paul mentioned. We've got to compute based on those sensors with verifiable, explainable AI models, and then we've got to take action with new robotics. So that's the new era, and it's not here yet, but that's indeed where we're going. And I like to call it a combination of global and local, because much of this will be done in low latency intervals with high capacity and high reliability at the edge. But then we'll be and that'll be helping humans in those localities, but then it'll be connected globally. So indeed, you can get larger perspective and indeed remotely interact with those systems to the extent you abide by the system requirements and latency intervals. So that's where we're going. And that's all about a productivity gain we're looking to achieve by digitizing the physical world. So if we move forward, this one, I think Paul touched on. This was an old McKinsey study, so I'm glad to see all the numbers converging. They estimated 4 to 11 trillion in productivity gains by the types of industrial automation Paul outlined and I've also alluded to. And those gains then would lead to investment in infrastructure. That investment in infrastructure is indeed the basis of the game. So you have to take that 4 to 11 trillion, and maybe 1 to 2 trillion will be invested in new infrastructures. It might even be more than that now, given the numbers we're seeing recently. And that'll result in 11% GDP growth. But to the left of that is a set of studies also done by McKinsey that try to identify the tasks that will be associated with that productivity gain. And the way to read it is the 6 different industry segments, which I've just picked 6 interesting ones, but they all can be divided into the same set of 7 tasks. And you can read the tasks: managing others, just a generic management, expertise management, stakeholder interactions. And then there's this very interesting 4 set, which is predictable and unpredictable physical work, and then data acquisition and processing. And that's where I want to argue those last 4, which, by the way, if you look at the color scale, those are the ones that can primarily be automated, with the hardest one to automate being the unpredictable physical task, which makes sense. If you can't predict the physical task, of course, it's very hard to automate it. But increasingly, as we can image and understand every aspect of our lives, and this is where you're going to begin to see the argument for UAS come in, if we can do that in real time and for every point on this earth that we can actually analyze and see and monitor, then the task no longer is unpredictable. In fact, it becomes well understood because you track its history, you apply some physics or mathematics or engineering rules to what you've seen, and you can predict the physical task. So then that says we can actually digitize and automate and increase the productivity of 60% of all tasks that businesses undertake. That's the the last four on this chart. That's a huge deal. So if you can ignore the trillions and the 11% numbers and the billions, just think of our quest with UAS. I'm going to argue at the forefront is to change 60% of our physical world by automating it and increasing productivity by doing so. So if we move forward, this is then the sort of COVID reminder, and I do like Paul's point there, but we learned a lot more than that we needed to remote learn. We learned that we wanted to remote everything and run our business and professional lives, as well as our personal lives, as well as our educational e-learning lives remotely. And in fact, what we discovered is, other than the diminution or attenuation of human social interaction, which we're all looking to recover, if you just put that one to the side and say that one needs to be addressed, the way of working in remote but digitally connected ways was very efficient. I know in my former company, there was a real concern that productivity would go down and that supply chains would be disrupted and manufacturing processes would be imperfect or compromised. But in fact, none of us really found that. We found, in fact, that we could work more and hopefully more efficiently by having access to all the resources. As soon as it was possible to have access to all the data and resources and tools that we typically had access to, we could work more efficiently by not having to commute, by not having to travel quite as much to meet each other. And there was a more facile engagement, and optimization became apparent. And I think that's true as long as we can solve for the tangible parts where humans feel disconnected. But again, that's where some of the haptic and sensory stuff, I think, does play a role. Can we immerse ourselves with each other that are almost equivalent to being there? If we can, then remoting, the ability to remote, inspect, see, survey, fix, is clearly the optimal way to be, because I can invoke any expert or any set of people from any point on the globe at any point in time, and that has to be optimal just logically. So now let's move to the argument for UAS. So yes, go ahead. I drafted this to say why, and this is what the panel is going to debate. So panel, get ready. I'm about to come to you. We're going to look at the world now in sort of a completeness and complexity paradigm. And I frankly just drafted this a few days ago. So take it as not exactly right, but perhaps instructive. So the way I look at the world is the completeness of the state information about everything I want to know. So you see that I define that in terms of local, global, and then monospectral, meaning only with one input, possibly visual or audio or whatever, or ultraviolet or infrared, and then all the way up to multispectral, where I can see everything across the entire sensory regime. So if that's one axis, and the other then is how many ways can I see that? From how many points of view, so that you obviously 1D, 2D, 3D, and then 6 degrees of freedom where I can see it from any point of view. And I would argue that where the popular press has been focusing on autonomous passenger vehicles is actually one of the simpler problems from a technical standpoint. And let me explain. Cars actually, I view as one-dimensional vehicles. They move one-dimensionally on highways, and then they typically make a turn and move one-dimensionally again. So they map a 2D space, but they do it in a series of one-dimensional operations. And yes, there's a critical spacing of those things, etc., but it's a one-dimensional problem. And then, of course, spectrally, they're really tuned just to sense the physical world much like a human would, which is largely video and some LiDAR-based, to do ranging, so ranging and video systems. So they're actually a relatively simpler portion of the space, mission critical for sure, and there are extreme safety concerns, but they're not necessarily where the hardest problems will be solved. So if we go to the other end of the spectrum, if you think of UAS, uncrewed aerial systems, that's really, they have the ability to see everything from any point of view, not just the linear point of view, not just the straight ahead view, but all around, which is not possible typically with autonomous passenger vehicles. And of course, they can carry a rich spectral array on board because they can be dynamically instrumented with any set of sensory devices, or different aerial systems can have different sensory devices that are circling around the object. And so you can get, in principle, a much more complete view. You can do it at all points in time, and you can do it from any point of view. And then all the other use cases, I will argue, are derivative in the sense you either remove degrees of freedom in the dimensionality standpoint, meaning how many points of view you record at once, or you remove spectral extent. And I think that's why I see UAS as such an interesting use case, because it's simply globally and locally applicable in the entire spectral regime and from all points of view. And if you could solve for that, you have complete knowledge. And so that's why I want to propose, back to the title of the presentation, is UAS the defining use case for both 5G and 6G? And if we can solve for that use case, we can solve for all the others, as long as we can do it rapidly enough that we don't miss those other use cases, which are equally important in different industries, but they're not as hard. So let's derive from the hard use case all the simpler use cases, rather than trying to do the opposite, start with the simpler ones and build towards the hard ones, which typically is a much harder route to take, because you make too many compromises with those simple use cases that don't allow for the future. So that's why I applaud OpenGen for focusing on the tough but critically important use case. So with that, that's the end of my little introduction, and it is my pleasure to introduce my panelists, who are actually much smarter and and much more engaging than I am. So they're going to do most of the talking from now on. But let me allow them to introduce themselves, and I'm going to do it in the following order. It's going to be Attila Takacs first. So over to you.
Yes, thank you, Marcus. So I'm Attila Takacs. I have an entrepreneur residence role in Ericsson D15 Labs in Santa Clara, California. I have been working in the telecom industry for over 15 years, mostly in the technology research side of R&D. I started my career driving standards development in IETF and IEEE. Then as a director of networking and cloud research, I led teams developing software-defined networking and network function virtualization, which are now core components of 5G. Then I helped establish Ericsson Garage, the company's first incubator in Silicon Valley, and then helped to grow it to 15 sites globally. Right now in Ericsson D15 Labs, I focus on new business opportunities of 5G, and I'm especially interested in robotics and autonomous systems out in the wide, and how cellular networks can enable these use cases. I've been involved in the UAS drone space for the last couple of years, supporting 3GPP standardization, as well as leading prototype development and POCs. In Open Generation, I am the chair of the Advanced Use Cases and Devices Working Group. And to close out with a fun fact, so last year when the pandemic hit and our office was closed down, it opened up a great opportunity for us to start a project and fly some racing drones over 5G in empty corridors. So this is the kind of work, if you wish, that you get by working at Ericsson. So thank you. Over to you.
Next up is Isabella Georgiza. Off you go, Isabella.
Hello. Thank you very much. And good morning, good afternoon, good evening, everyone. So my name is Isabella Georgiza, and I'm a principal communications engineer at MITRE. My work includes analysis, modeling, and simulation in aeronautical communication systems. My areas of focus include air-to-ground communications, aviation standardization activities, airport surface communications, and most recently UAS. More specifically, looking at the connectivity for small UAS or drones. In terms of my prior experience, I have worked in wireless terrestrial network design and optimization, and also in SATCOM R&D. So it is really exciting to be here. In terms of one exciting part, this is my first panel, so thank you for including me.
You don't look like it's your first panel. You look like an old pro, a young pro. And now over to Phil Burks, a legend. Phil, introduce yourself.
Legend, thank you, Marcus. Legend means old, which I was sitting thinking about how to introduce myself. You know, the word former comes up an awful lot, and the older you get, the more the word former comes up. But what is still current with me, I am fundamentally a lazy person. And I worked hard to try to be lazy. I do have a degree many years ago in electrical engineering, which means I can legally tell you where and how hard to kick something to make it work. have for about 32 years had a software company here in Tyler, Texas, where we're located, where we have done software to help for performance management solutions for Motorola two-way radio networks around the world, the P25 networks, Mototurbo, and other networks globally. We've got over 900 customers that start with the city of, the county of, the state of, and the province of. And we're real proud of our 50 folks that we have here. We had an idea that came together to coalesce several technologies into a thing called First Eyes to provide an autonomous drone solution for our first responders. But that also then moved forward into several other silos of marketing and income, and for border security, for other securities around campuses and so forth. And we've got some other areas that will probably come up in the conversation. But anyway, I'm glad to be here and so excited about what we're going to be doing all together to promote 5G and how we can save lives and save time and save money as we go forward.
And by no means least, we have Eric Ringer. Eric, over to you.
Hey everyone, I'm Eric Ringer, Chief of Staff of the Robotics Business Technology team at Verizon. We work on both air robots, drones, as well as ground robots, air robots through Skyward, and then ground robots through a company we recently acquired called Incubed IT. Coincidentally, I'm in Austria today, talking with you all from a lovely hotel room as I'm visiting with that team. I came to be a part of Verizon first by co-founding Skyward, where we had a dream of changing the way that people access the world. We had this dream that you could get to know the world, see the world in the same way that pilots do, and that you could use that productively to increase productivity just by clicking a button. We've got a ways to go still before we can get to that promise fulfilled on clicking the button. But a big component of it is networks, being able to talk with the robot from anywhere, be it on the ground or in the air. And we've got some exciting things ahead. We've got 4G drones on the network today. We're innovating with MITRE on 5G and proving out the performance of 5G to help us take those use cases above and beyond to prove safety cases in a lot of rich application areas that we heard about earlier from Paul. In my time with Skyward, I have worked on just about any major use case you can think of for drones: construction and engineering, mining, energy and utilities, telecommunications, etc. And I've also advised Fortune 50 companies with multi-billion-dollar supply chains on how or if they even could use drones in their current state in those. So I love the robots. I love them all, air or ground. And then I continue that work on the decision board of the Aerial Connectivity Joint Activity between GSMA and GUTMA, where we're trying to harmonize these two big industries and bring some terminology together so that they can speak each other's languages and standards, as well as in actual technical applications.
Okay, that's the panel. I think you can all agree it's a fantastic panel. And so now we're going to start. We have a set of questions that we're going to run through. We have not rehearsed answers, so it hopefully is going to be as to the poll questions that are coming in as well. But to get things started, Eric, I'm going to start with you because you made the claim that you have worked on all the use cases. I don't think you said quite all, but so many. Just about all the use cases. So Eric's going to start. So my first question, this is, we're going to just throw out, and then all of you can take a stab at it. And we're going to be nice and agile and dynamic, so anyone can jump in whenever you feel like it. But the first question is, do you agree that UAS is the most challenging use case from which all others can be reasonably derived? If yes, why do you believe that? If no, why not? Over to you, Eric.
I'm going to go contrarian off the bat and say no. I agree with the framework that you laid out, but we have one advantage in the drone space, and that is that most of the things that a drone can run into are on the ground. They're mostly all the same things that an autonomous car could run into. So we do have the ability to get into the air and fly with some freedom, which definitely decreases the technical challenge a bit. We do have other technical challenges like how to make use of terrestrial networks for airborne devices, how to spot aircraft, big consequential things that are moving that we might need to be able to maneuver around or get out of the way of. But by and large, that freedom of movement is actually a pretty big advantage when it comes to navigating.
Okay, as moderator, I have to object to your objection. But what I will throw in there is, if we included the indoor use cases in the definition, which we've all alluded to, then surely my aerial dimension and my people dimension or terrestrial dimension converge a bit. And so now I'm back to it being the hardest use case. Fair or not?
Yeah, that's definitely fair. Definitely gets a lot harder indoors.
Okay, who wants to build from Eric or oppose Eric? Attila, off you go.
Yeah, so I think it's a interesting question. I don't want to say yes or no, but I want to highlight one thing that is very different for the US that we don't see in ground vehicles or autonomous cars, and that is that this is an industry which is used to have traffic management and coordinate airplanes in the air by some sort of control towers or mechanisms and policies. And this is not something that you traditionally have for cars. And because of this, I think this is a unique characteristics for UAS or airborne traffic that help us see what the future might bring. So if you are thinking about autonomous robots out there in the wild, you will have to have some system that is keeping track of these robots. Whose robots are these? Where are these? Who are operating them? Who is responsible for them? And once you remove the human pilot or the human from device, you will need to have a system that is keeping track of all of these devices. And I think if you crack the US case and we understand how regulations, management systems, insurance work together, I think this will help any kinds of robot to actually move forward faster in the future. So if we have
a really interesting point. So let me just jump in there. So if you're arguing that we need to solve for the control plane, that it's sophisticated enough to understand the entire flow of what is the high dimensional space and many actors, because there's the takeoff, the landing, the transport, the delivery, the surveillance, whatever. That perhaps is more sophisticated a view because it's collective and coherent than the idea of autonomous vehicles on the road, where it's essentially just to avoid each other, avoid colliding with each other, and then move as you would see fit, which is very different from the drone case, which has to be managed and coordinated. So, but we need perhaps a control plane to solve for the car case as well in the end. Is that the argument you'd make?
Yeah. So my point is, once you remove the pilot or the driver, you need to have some other system that is overseeing this whole vehicle, right? Be it a car, be it a drone. And if you remove people altogether, so if there are no passengers, there is nobody who is calling in an accident, right? So you need to have some other system that is taking care of all the other things that usually humans are taking care of. And I think this is, and the US is actually very unique in the sense that this industry is used to have these type of systems. We just have to generalize them and make them sort of ready and improve it with technology. So remove the voice, remove the pilot, remove the human controller, and make everything automated.
Very good point. So Phil, to you, do you agree that the control plane is a critical differentiator, and it's in the end how we will have to solve for all these use cases?
I do, and love you, Eric, but you're wrong. I think the UAS is absolutely the most important and most challenging because as I mentioned in the opening, my point of view is one of our biggest and best uses for UAS is in our public safety world. There was a study done in 2017, I believe it was, by the FCC that said if we can shave 1 minute off of every 911 response in America in 1 year, it's equivalent to saving 10,000 lives. That's huge. To do that, we need a good, high quality, reliable network that's going to allow the communication anywhere with 24/7, 365, 5 nines of reliability. And as I pointed out in something I was saying earlier, C2, our command and control, is the most important thing. That has to stay up 24/7. And we also then have our payload and telemetry, which has to stay up 24/7 because we got to be able to see what's going on. And if we have number one without number two, we got nothing. If we have number two without number one, we have nothing. If we have the two of them together, it's 100%. It's challenging as all get out. And I think we can conquer that. We can derive everything else.
Eric, we have to give you a chance to respond.
Yeah.
You ended up agreeing with us somewhat.
Somewhat. I will say the complexity, though, of knowing what is around you and how to navigate in the open world is definitely a lot harder when you can't control for things. So in the outdoor space, it's much more difficult, I will say, on the ground than in the air. On the indoor space, theoretically, you have some control over that environment, and you can map it pretty routinely. It's a lot easier to maintain a database of what's there. A couple of years ago, I was talking with some colleagues that work for the city of LA, and they were talking about some of their digital infrastructure initiatives where they're trying to catalog every piece of road infrastructure that they have in Los Angeles. And it's not static. It changes, it updates, and trying to keep track of that so that they can have this catalog ready to be able to communicate with autonomous vehicles, so they don't have to solely rely on the sensors on board the vehicle to be able to read a stop sign in a human way. That sounds so difficult. And I'm really, I feel good that I'm more in the drone side of things, where there's just a lot less of that infrastructure. We have a lot more of a pun intended blue sky in front of us as far as infrastructure to build.
But just to build on that a little bit, and then we'll go to Isabella, isn't one way to capture that information, the stop signs, the trees and foliage, etc. Because again, my many points of view, I can get satellite imaging, I can get a street view image that's maybe 6 months old. But actually, most of those use cases require me to know, is the pothole there from the day before or the hour before, or the tree in foliage or not, or the light's been knocked over, whatever it is. It's sort of minute by minute that I need to know. So isn't a drone the only realistic way if I'm not already instrumented everywhere, which I won't be?
Not, I would say a drone is a participant in that system. Every other autonomous vehicle on the road is a participant in that system as well. The lighting conditions can significantly impact the vehicle's ability to read something that is out in the road. But all of those use cases, being connected on the network and being able to transmit the data to that repository that's maintaining it and applying analytics on it to decipher what's new and what's not, all of that is good. All of that crossover, excellently applied to all of those.
It's a good point, because in the end, let's think about the drone as a use case in some complete scenario. It's going to interact with a person to get a payload, almost certainly. It's going to be in the clutter for the part of its flight where it just takes off. And then, of course, it might be, as you say, in the more controlled environment, right? Or the less controlled environment, but less cluttered environment, which is the space. But then it might actually be on drone highways. And then, of course, it has to reverse that at the other end. So I do like your point that if we combine drone with its input and its output, meaning when it takes off and lands, and that interaction, then that completes the scenario, I think, quite nicely. Is that fair to say, Eric?
Yeah, I think so.
So, Isabella, time for you to say something. What do you think so far?
Yes, I mean, I think the discussion is really interesting. A couple of points I would like to add to it is that we do need to enable the safe large-scale integration of drones in the NAS, and that's where the experimentation that OpenGen will enable with collaboration from everyone involved will really move things forward and include the test beds, the environments, the different operational environments, as well as the different just topography that we will be able to experiment in and take measurements and then analyze the data. I think it will actually make a big difference and to enable the safe large-scale introduction of drones and beyond visual line of sight operation also at large scale and safely in the US NAS.
Well, Isabella, you've led me a little bit towards my next question, and a question coming in from the audience as well about 5G features that are critical. But let's just mention in passing, for those of you who haven't kept up with OpenGen, they have secured 100-mile flight path, so 50-mile there and back, and then a 5G testbed location within that. And so there will be the ability to test this entire use case of picking something up if we talk about the delivery case, so you could actually be just picking up your spectral imaging system. It doesn't have to be a good flying, both in a local 5G enabled hub and then over an extended area of 50 miles long, doing something in that space, and then either returning to a different destination or the origin. So that is the entire loop that I think it's the first time, particularly with all the industry participants, we'll be able to access that space and explore the full complexity and richness of the UAS case. So, Isabella, I'm going to start with you since you got the last chance. This time, why is 5G critical for UAS is the next question, and it was a question coming from the viewing public as well. So what aspects of 5G, I should say, are critical for UAS?
There are so many. So let me start with a few, and I'm sure all the colleagues will include many others. So the ability to have low latency connectivity, I think this will be, and reliable connectivity as well. I think that will be very important. It was mentioned for the C2 link for command and control, but also as part of possible future detect and avoid solutions. Having high throughput for real-time high-resolution video, that was just mentioned a couple of minutes ago, and it was mentioned earlier in the morning as well. Network slicing, I would say, is going to prove very important as well. So, I mean, these are just a few. There are many more than that.
So next then.
And of course, MIMO and beamforming.
You just listed all the 5G attributes. But let's go to Phil. Phil, what do you think?
Yeah, well, it is. There's no question about it, because our goal is to act like, have the UAS act like there is a person right there. And the best way to do that is with extremely low latency, extremely broad bandwidth, so that a remote operator for a UAS can sit there with a virtual goggle, look all around, see everything that's going on while the drone is flying from any height, any elevation, while the whole time, what if we could get it to the point where we have sensors on the drone, and while it's flying, he or she can smell what's going on. And using all the senses that we have around.
Smell in a generalized sort of chemical receptor way, not necessarily a human nose way.
Correct. Yeah. Yes. I mean, so we can say presence of methane, presence of ammonia, and we can do that. We have the technology to be able to do that. Now, I'll be I'll say something controversial because we're all about 5G here, but is that 5G? Is it 6G? Is it direct to satellite? I don't know. But I can tell you from the use cases that we're around, it has to be reliable and it has to be really low latency.
Attila, do you want to add to that? To the idea of the drone, the UAS case has to be person and drone in close proximity is sort of the ultimate test case, which is correct because, of course, drone in close proximity to mechanical system has some obviously security and stability and let's say operating issues, but next to a person is even more critical, wouldn't you say? So do you like that case as the defining one? If so, is 5G critical for that rather than LTE?
Yes, I think there are a lot of different use cases and applications how you control the drone, right? So you can direct control, low latency, so that the human is sort of in the loop and interacting with the drone and the environment that the drone is in. And there are other use cases when you can lighten the drone and all the control and the smarts of a drone is actually offloaded to the network. These are the typical edge use cases, which again require low latency and close processing somewhere close at the base station. But there are also use cases where the drone is smarter and there is more sort of autonomy on the drone, and you can have relaxed latency requirement, but still you have a requirement to have reliable connectivity. So my argument is that 5G is critical, and it is critical because from 4G to 5G, we are actually not just adding bandwidth and latency and more features, but there's also a mindset shift in the industry that now we covered mobile broadband, we connected people, and now we are focusing on machines. So there's a lot of discussion about IoT. It started in 4G, now there is more in 5G, and not just IoT, but we're also talking about critical communication, ultra latency communication, and industrial applications for 5G. And I think this move to really include and connect devices and robots is actually what makes 5G critical. because now the whole industry and 3GPP and the standardization bodies and the companies who are playing in this ecosystem are thinking about how to improve the connectivity for this type of applications. I think the critical piece for drones and 5G and also later for 6G is to make sure that these different applications are coexisting in the same network. So I think the major question is not really about latency and bandwidth in my mind. It's more about how we can use the existing public infrastructure and make sure that existing users are not impacted. So how we are handling interference with ground users from drones and so on, without the need to redesign the already deployed network. So there's sort of an economic question about how we can use the existing infrastructure and make sure everything is happy and everything works perfectly fine. And beamforming, as I mentioned, is one piece of the equation to make this work.
So you touched on the idea of network slicing, meaning sharing an infrastructure and giving prioritization to different flows. So I'm going to throw that back to Eric, but I also ask Eric a question related somewhat, which is what functions will the drone be allowed to perform itself truly autonomously, in your view, versus always having to check with a command and control system? Obviously, there's the case where the command and control system is dislocated or disconnected from the drone. It has to be able to sort of invoke a safe operation procedure. But really, I'm talking about when the situation is that there is connectivity, what will the drone autonomously determine, and what will be subject to a command and control system? And then that relates to the use of network slicing, I think, in a way of what does it always need to have available to it across a network. But Eric, over to you. Yeah,
when we're talking about autonomy, a lot of it depends on, I think, the architecture of the system that the drone manufacturer enables. It's really about where they're going to put the smarts. Is it going to be on board the aircraft itself, or have we proven enough reliability in the network that more and more of that can be offloaded onto parts of the network, such as multi-access edge compute? I think that ultimately a certain amount of the smarts are still going to need to live on board the drone. We can't take it all out because inevitably there are going to be cases where the drone needs to be able to still get around in case of losing a link. It needs to be able to execute on certain types of commands. But it can also use some of the other infrastructure around it, like with CV2X, to be able to help navigate in that space.
Can you give us a number for how close a drone, in your view, will be allowed to access an object when it's disconnected from a command and control system? I know I'm asking you to generalize something.
Yeah, I'd be projecting into the future quite a bit, and a lot of it will depend on regulations and what we can prove technically. But I will say that we've seen a high degree of correlation of the more rural or the more absent people are. So if we can reduce ground risk and we can reduce air risk, then a lot more is allowed. So I think with static infrastructure inspection for things like, let's say, substation inspection, where you've got a perimeter fairly well secured and you're flying perhaps within the confines of that infrastructure, so you're pretty sure that there's not going to be another aircraft coming into that space, theoretically you could do a lot without necessarily being connected to the network as far as collecting information about it. Now, assessing what's actually wrong, that probably needs quite a bit more compute power. So you actually do want to be connected to a network to be able to access that compute power. But one important thing that I want to make sure that we address is that there's a lot that we can do with 4G today. 5G is still being developed. We are deploying the networks right now. And the power of what we're doing with MITRE Open Generation Consortium is defining the use cases and getting the technology experts together to actually go push the limits on what 5G can do, so that as we're building those networks out more and more, we can deploy them with these use cases in mind.
Well said, Eric. And of course, the idea of the flight path is that it'll be predominantly an LTE region just by sheer deployment density with parts of 5G, and then increasingly 5G will be added. So the handoff between LTE and 5G, as well as the going beyond line of sight and managing that, is what you're referring to, I think, is a critically important problem. I agree.
And Marcus, let me Eric, I like you a little bit better now. I mean, you're coming around. But as we're building this stuff out, we have to remember beam tilt. Right now, what 5G and others are out there are tilted down. We're going to be up above that. So as we're building, we have to remember to allow that coverage up above the ground.
What gets complicated?
Go ahead, Eric.
What gets complicated in 5G is that we're actually dealing with 3 different types of physics for the beams themselves. We've got low band, mid band, and high band, where really in 4G, we've mostly just dealt with low band. So that adds a certain degree of complexity, but that's also where a lot of the capability comes from. And knowing what we need and when and where, and what service can be provided where, is a pretty important part of enabling a lot of these drone operations. And in some cases, with network slicing, that's how we're going to be able to deliver certain types of service levels to certain types of use cases. And Phil, you were talking about earlier about emergency response, a highly important use case that has high demands. And we need to know it's resource intensive on the network if all those demands are there. So we need to make sure that we know that we can build that up, and then we can deliver it, and that the networks can function from a business perspective to deliver that use case.
Well, I want to come back to your point, Eric, about where the compute resides. Of course, the more efficiently you can analyze the scenario locally on board the drone, so with advances in compute and new imaging processing technologies, then of course the drone to some extent can self-determine and just send a video stream back, or a composite stream, I should say. It's not sending the entire data stream, it's sending just the analytical data needed, which then can be rendered perhaps without having to transport the entire video feed. Because I agree, if we're sending high definition video feeds from a mass of drones that are analyzing things from all angles, then of course even the best 5G network will become compromised, probably just because of this, the signal strength and throughput you'll have on each of those links, flying as you are. So I think it is true that we have to optimize for the process what you can on the drone in order to be as self-reliant as possible, but also to minimize backhaul bandwidth. But in the end, command and control and higher order analysis is going to be required in most cases. Is that a fair summary?
Yeah, I think so. Well said.
All right, Phil, do you want to add anything apart from your?
The other thing I was going to add into this point is that one of the other things that's happening that we're seeing in drones is AR overlays. Where we have, as the drone is flying, we have the video coming back, but we're also then overlaying augmented reality to it to say, here's a fire hydrant, here's a highway. So
you're doing the live analytics to augment the feed coming back.
Precisely. So again, it's another need for extremely high reliable, extremely low latency information passing back and forth. And to your point, Marcus, we've got higher, it seems like every couple of months, there's a higher power processing that we can put right on the drone. So we are making strides in that, but we just cannot stress the importance of keeping that C2 link as strong as we can.
So I'm going to go off to another aspect of this, and the power requirements. So actually, I want the flight duration. What is, because flight duration, of course, is a part of this equation that says if I put a lot of processing in the drone, I'm going to drain its battery. So its flight duration will be compromised. Also, having a radio link, of course, maybe I can make that spectrally efficient, and that's lower power consuming. But what's the right answer for flight duration for a drone in your view, and how do we solve for that?
Yeah, I'll take that one real quickly. What we all try to do is we're trying to make this as hands-off as possible. There are hybrid drones that have onboard generators, and those guys can last for a long time. There are tethered drones. They can last 24 plus hours. In both of those cases, it's not a big deal. What we are been pressing down is the fully electric drone, where it can charge itself, it can take off itself, etc. And the answer there is there seems to be a sweet spot roughly around an hour, because by that time, hopefully you've got boots on the ground and you've got other things answering. For long-term surveillance, we're seeing 2 hours that can be done. So that's the quick answer for you.
Eric, any comments?
With one of our multi-rotor friends in the industry, we talked with them about the potential of 5G, and I was trying to get to the root of the power savings that could be had by removing some of the onboard compute, because they have a pretty sophisticated Qualcomm processor on there, and I thought, you're doing a lot of AI on the aircraft. That's got to be expensive power-wise. I said, actually, no, not so much. If we were to take that off completely, it'd be about 10% power savings on a 22-minute flight. So That's about
2 minutes.
2.5 minutes. That's good, but that's not like worth upending your entire architecture.
Attila.
What about removing an engine, right?
What is that?
Removing an engine, right? You can save more by having less engines on the road.
Yeah.
Yeah, if you can get an aircraft and there's a bunch of them out there that are hybrid VTOL using the wing, and the wing itself takes over and gives you the lift, and you cut down on your motors. Your motors are by far Eric, probably the other 80% of your drain. So putting computing power on it and radios is probably at the lower end of the spectrum.
10% savings are not defining of a change in architecture, I think, or don't drive a change in architecture. That's probably well said. Isabella, any comment from you?
Regarding the architecture, I was just thinking about that, and the comments before that we have to, in experimenting, to also look at the impact of drones on the terrestrial users as well, to reduce any interference that may happen, and the architectures that will be enabled and will be analyzed and experimented with. Different kinds of architectures will also be important for this.
Good. So next question. We've got about half an hour left, and we've got 3 or 4 questions. So quick one for each of you. How important is the flight path that I've mentioned, the 100-mile flight path that OpenGen is working on, and then some others that are smaller flight paths? How important is that? And in that flight path, working on real use cases that span the entire ecosystem of which would be drone maker, sensor maker, network equipment maker, network provider, AI system or cloud or computing platform, and AI system provider, application provider. Do they all have to get together? And if so, is the OpenGen flight path the place to do that in your view from all your experience? So I'll start with Phil.
Absolutely. The FAA is kind of our master in this whole thing, and they love seeing data. And there's nothing better to present them safety case data than